Okay, today we're going to be talking about combination circuits. So these are circuits that are going to be a combination of some combination of parallel and series circuits. So we could have something along, so you could end up with a lot of different varieties of, circuit diagrams. You could have something that looks like, that would just be series. Here would be series and parallel. So you could have something that looks like this. You could have things here. You could have two sets of parallel and one set of series. There's all sorts of things that can happen. Uh, when we're doing this, what we're going to do is we're going to think about groups of resistances. So first thing that we're going to do with this is we're going to calculate our resistance. And this is our total resistance actually. And when we do this, I'm going to say, note the resistance on parallel circuits, on the parallel pieces, because that is going to be fairly important to us later. So say I've got something like, say I've got a circuit like this, and I'll do like 24 volts. I'll say we've got 8 ohms here and 4 ohms here, 4 ohms and 12 ohms here. And I'm going to point something out that you might not have spotted, and I'll give you a different thing. If you've got, especially if you've just got a parallel circuit with two different things, uh, I'll give you a different formula for this if you've got, but let's show you what we're going to do here. So when I look at my resistance on this total circuit, I'm going to see that for my series pieces, I only have this one piece that's in line, and these are my parallel. So for my parallel resistances, now I'm going to note that, so I'm going to just basically say, well, what would happen if I were just to look at my parallel? For my parallel resistance, remember that's equal to kind of 1 over the sum of the reciprocals. Now, one of the things I could do is I could multiply these by the common denominators, and I'm just going to show you a quick shortcut with this. If I were to do something like, say, multiply this by, say, 4 over 4, multiply this one by 12 over 12, and I know that's not the common denominator. Or it's a common denominator, it isn't the smallest denominator. But what we're going to end up with, what we'd end up with is, 1 over RP is equal to, gosh, 12 over, and I'm going to just leave that over, 4 times 12 plus 4 over 12 times 4. And hey, I got 1 over my parallel resistance is equal to, 12 plus 4 over 4 times 12, which means that my parallel resistance is just the product of those over the sum of those. And in fact, if I were to call this, you know, resistance B and resistance C, I could say that I could in fact say that my parallel resistance is the product over the sum. It gets more complicated when I have a third piece in there, so I'm just going to do this with 2 for now. But this would be my parallel resistance. And let's show you now another, but now I'll just go ahead and add this up into this. So I'm going to continue on with this, calculating our total resistance for this. So here this parallel resistance This parallel resistance would be 4 times 12 is going to be 48 over 16. So that's going to be, so yeah, my parallel resistance is 48 over 16, which would in fact be equal to 3, and this is 3 ohms. So my effective resistance for this piece is 3 ohms, and that means that my total resistance on the entire circuit, my total resistance is going to be my what I have in series plus what I have in parallel. And if I've got more than one parallel piece, then we'll have to add those up separately. So this is going to be that's my series resistance plus my parallel resistance. So in this case, my total resistance is going to be, that was like 8 ohms plus 3 ohms. So I've got a grand total of 11 ohms. So that first part, calculate our total resistance. Now that we've got our total resistance, we're going to, so we've calculated our total resistance. We've got that. Step 2, we're going to calculate our total current. So our total current is just going to be our voltage. Now, this is where our Ohm's law comes in. And remember, for some folks who like this, you get this V IR, or if you prefer, V equals IR. When I'm calculating my current, that would be my voltage over resistance. So yeah, my total current is going to be equal to my voltage over my total resistance. In which case, my total current here is going to be 24 volts over my 11 ohms that we came up with before. And we're going to end up doing some rounding, but okay, 24 divided by 11. This is going to be about 2.2 amps. So my total current is 2.2 amps. And now that we found our total current, now we get to go back and figure out what our voltage drop across each of these resistors are. So we've calculated our total resistance, we've got our total current. Now we're going to find our voltage drop across all of our resistors. And this is where those parallel versus the series pieces are really going to be important. So for our voltage drops, for our pieces in series, we're just going to use the current through the resistor. We're just going to use the individual resistors. For things in parallel, we're going to use whatever that effective resistance across the parallel circuits are. So for our circuit here, we have 2.2 amps. So I've got my total current, and if I'm looking at across my resistor A, well, V equals my voltage across resistance A is going to be that my total current over resistance A. So this is going to be my voltage across A is that 2.2 amps times that 8 ohms. And this is going to be 17.6 volts. That's my voltage drop across A. So this was my one thing I had in series. Now I had two in parallel. And the funny thing is, my voltage is in parallel. I am going to say, well, the the voltage is going to drop the same across both of these. So with my parallel circuits, or with my parallel resistors, I'm going to say, okay, well, my voltage for that parallel piece is going to be the current times my resistance in parallel. So in this case, my voltage drop across my parallel circuits is going to be, it's going to be that 2.2 amps, but it's going to be across my parallel resistance. Because effectively the resistance is lower across parallel circuits. So here my parallel voltage is going to be 6.6 volts. Now that means that I'm going to have voltage drops. That means that my voltage drop across B is that 6.6 volts, and it means my voltage drop across C is 6.6 volts. And now that we have our voltage drops across all of our resistors, now we can figure out what the current through each resistor is. So our last step with this is we're going to calculate the current through each resistor. Now remember that again, now I would have current would be equal to my voltage divided by my resistance. And in this case, I know what each individual current is. I know what each resistance is. I know what the voltage drop across each one is. So with that, it's a fairly simple, straightforward calculation. My current in A would be equal to my voltage drop across A over my resistance A. And I had already said that, it was, my voltage was that 17.6, and my resistance was 8, which means that this is going to be 2.2. And that makes some sense. Oops. Yeah, 2.2 amps. Because in that circuit, so remember in this original circuit, everything, all of the current is passing through this initial thing, which means that having the total current be through this resistor be 2.2, that makes a good deal of sense. And of course, our voltage drop in this one was at 17.6 volts. Okay, for resistance B, Our resistance in B was 4 ohms. Our voltage drop was 6.6. So our current, we can figure out our current from that. Same thing with our resistance C. This was 12 ohms, and that voltage drop was 6.6 volts. Okay, well, current through B is going to be that voltage drop in B over my resistance B. So in this case, that's going to be 6.6 divided by 4. And we're probably going to end up with some some longer, well, actually, no, it won't be. Here, this current is going to end up being 1.6 amps. So that's my voltage, or sorry, my current across B. And last but not least, we've got our voltage drop in C, is that resistance C, or that voltage in C divided by the resistance in C. So that's going to be that 6.6 volts divided by my 12 ohms. And here you might end up needing to do a little bit of rounding. This shows up as 0.55 amps. And yeah, that would probably work. We could, depending on what the tolerances of the system are, you could probably enter that in as 0.55 or 0.6. But alrighty, there we have it. This is how you go through calculating all of the pieces, each individual piece that you're going to need for a particular circuit. And all we started with was our voltage and our individual resistors. So remember, what we did first is we calculated our resistances first, and we found our total and kind of the effective on our parallel. We found our total current. Then we found our voltage drops. And then last but not least, we found the individual current. Alrighty. I think that is enough for right now, and we will see you in the next video.